Is it okay? So, hello everyone, welcome to this first meeting of this year. Today I have a pleasure to introduce the talk by David Stewart from the University of Manchester. The title of his talk is Geometrical Rigidity of Modules for Algebraic Groups.
Many thanks. I hope I'm using OBS, so there are enough bits moving that I would something may go wrong. So do let me know if you can't see anything or hear properly, and then I will see what I can do about it. I should probably start by saying Happy New Year to everybody, and let's hope it is somewhat better than the last, which is probably unlikely, but there we go. So I want to talk about some work that I have done recently with joint with Mike Bate, who is in York. And it's about looking at the structure of modules, representations for algebraic groups as you apply base change. So as you move from a smaller field to a bigger one, and what the result of that is. And I am hoping that I will manage to get through things in enough time to be able to ask a question towards the end. It would be fairly unlikely, I think, if you took around a bunch of people that they would have anything to say about this, but I might just get lucky, so I will ask it. So the story that we have starts with just an algebraic group, an affine algebraic group. So we let G be an affine algebraic group over, I'm going to say K, which for almost all of this talk is going to be a field. So I will write a field, but also towards the end, and I suppose there are other points, but towards the end, I will also want to think about the case where K is a just an arbitrary commutative unital ring. So we will bear that in mind. So I don't know how familiar people are with it, the theory of algebraic groups. So I will, if we're over just give some very basic background. If we're over a field, and just to be very just to dot every I and cross every T, I should let's ignore that. A more illustrative example. So with these conditions, so with these conditions, we can find a faithful representation, and that means that we can consider G to be a subgroup of the invertible endomorphisms on some vector space V. So, V, a vector space of finite dimension, over K. And it's Zariski closed. And that means that you get you cut out G from the matrices that represent these elements by putting polynomial conditions on the entries. So, uh, so G is the subgroup uh, of matrices satisfying some polynomial condition, some polynomial conditions. So the classic example is where we take the determinant, and we know the determinant is a polynomial in the entries, and so we could do something like insist that the determinant is 1. So a very good example is SLV, because that is where we set the determinant of the matrices we're looking at to be equal to 1. Okay, so we want to start saying things about the about these groups. One thing that we realize very quickly is that we can't say very much at all about the class of unipotent groups. So let me just say what those are. So we say G is unipotent if it is isomorphic to a subgroup of upper triangular, strictly upper triangular matrices. So for some, for some dimension. So just like P groups are completely wild, unipotent unipotent algebraic groups are completely wild. And so if you want to say something complete about algebraic groups, you need to get rid of this somehow. And so the way we do this is by insisting that there is no normal subgroup like this, or more specifically, so if we I'm going to say what happens over an algebraically closed field, because I'm going to then contrast that with what happens over an arbitrary field. So if K was K bar, we say that Ru of G is the unipotent radical of G, and it is the largest, and I will say I'm not going to talk too much about the issue of smoothness and related matters, but I will just write the word down. It is the largest smooth, connected, and normal and unipotent subgroup of G. And okay, so that's the definition of Ru of G, and we want that to be trivial. So G is reductive if it is connected and smooth and the unipotent radical is 1. So there's no there is no very significant piece of unipotent subgroups sticking out of this. And then what's incredible is that you, with just that condition of being reductive, you can write down a complete classification, and this classification is entirely independent of the characteristic of the field. So amazingly, we then have a characteristic free classification of the possibilities for G. Right. So what about if the field is not algebraically closed? So one thing that you can do when you're investigating algebraic groups and schemes in general is to look at the way that to look at forms of them. Things that when you extend to an algebraic closure, you know what that looks like. That you try to understand how the Galois group of that extension is can be harnessed to tell you about the possibilities for isomorphism classes. And if you go down that road, then you end up with all this TITS classification with the various diagrams, Dickin diagrams with indices above them. That works very difficult, but it does it does work in principle as long as the field extension that you have that you're working with is separable. And if it is not separable, which means that the field K you're looking at is imperfect, then you get a whole different kind behavior that you have to deal with. And that's where you come across the idea of a pseudo-reductive group. So more generally, for any K, let so RU K of G be the K unipotent radical. So that is the largest. It's all the same stuff, smooth, and I will just put dot 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 because it's all the same, except instead of subgroup, I just put K defined subgroup of G. And I will give an example of one of these groups. Sorry, missing something. Right. Largest thing, and then we say that G is pseudo-reductive. If it is connected and smooth and RUK of G is 1. Okay, so this is this notion, so pseudo-reductive. Okay, so what do I want to do? So I want to make a couple of observations first. One is that the definition of the largest smooth K-defined subgroup of G, that is a characteristic subgroup. And so if you have a Galois extension, then the sort of general theory of Galois descent kicks in, and you can see that you can descend the unipotent radical of G over an algebraically closed field down to this K. So if the extension K bar over K is Galois, you can do this Galois descent. So the only time that this is a different notion is when uh, K bar over K is uh, inseparable. So you have to be therefore in the situation where K has characteristic P, and it can't be a finite field. So uh, it is somewhat uh, specialized in that respect. Uh, let's have an example. So uh, these groups are very, very closely connected to Weil restrictions. And a Weil restriction is where you have a field extension, you consider some algebraic group as sort of defined over the larger thing, and then you look at it as if it is a group over a smaller thing. Uh, at some level, really, what this is doing is just kind of decomposing a vector space over K dashed some larger field as a vector space over K. So that's the sort of idea that goes into this, but let's try and be extremely explicit. So let K, this will be our base field, and I am going to take a function field over FP. So I need something that is nice infinite. So we just take polynomials over FP and then take the fraction field. And then I let K dash be the classic kind of inseparable extension that you see when you're studying Galois theory. So it's just going to be FP U, where U is a pth root of T. And then I won't explain this. I'm sure everybody knows that has seen this before. K dashed over K is a purely inseparable extension. Okay. And then let's take the simplest reductive algebraic group we can think of, which is the multiplicative group of the field. So let G dashed be equal to, so just the multiplicative group of the field over K dashed. So if we're thinking about things in terms of points, and we may as well here, then I'm going to identify G dashed with just the non-zero elements of K dashed. So that's the multiplicative group of the field. And then we look at this group as if it were a group over K. And as I say, really that comes down to sort of decomposing a vector space. So G is G dashed, but viewed as a vector, as a group over K. Okay, and my claim is that this is reductive. Sorry, this is pseudo-reductive, but not reductive. So claim this is pseudo-reductive, but not reductive. Okay, so let's first of all observe that it is pseudo-reductive. So we have just this field k dashed where we're looking at all the non-zero elements. It's a field. So if I want any unipotent elements in there, they are going to have to be elements for which the p power is 1. But so the polynomial, well, there would have to be solutions to the polynomial of this flavor. So x to the p minus, well, x to the p equals 1 would have to have solutions if G had any unipotent elements at all. But K dash is a field, and if we're trying to solve this polynomial equation, there's over a field, there can only ever be one solution to this because it has a factorization that sometimes gets called the student's binomial theorem, because it's looks very similar to the mistakes that students make. So this is equivalent to x minus 1 to the p equals 0, and then that only has one solution. So there are no non-trivial unipotent elements in G at all. So it certainly has to be pseudo-reductive. So certainly this is pseudo-reductive. But it's not reductive. Reductivity is determined over an algebraic closure, but I can do something that's even simpler. So note, though, if I take k dashed to the p, so I take all of the elements in k dash to the p, then the all of my polynomials, which are in U, they now are in here, they're in U to the P, and U to the P is T. So taking the P power map just pushes me down into K. Right. So if I look at G dash, G, which was this field K dash, the invertible elements considered over K, this quotient, so K dashed obviously embeds inside K, obviously embeds inside K dashed, and so you get this, you can take this quotient. This is an algebraic group, which is now killed completely by the P map, because everything in here but by the taken to the P is pushed into here. So this is a quotient of G dashed, which is entirely unipotent because it's killed by the P power map. And then you can go back and think of your the classification that you know of reductive groups over algebraically closed fields, and you know that they do not have unipotent quotients. So reductive groups do not have unipotent quotients. Right. So that's the sort of thing that that's the basic, the very most basic example of how you produce these pseudo-reductive groups. You take inseparable extensions and take Weil restrictions. There's a huge amount of work that done very reasonably recently. I think around 2010, the first edition of the book came out by Conrad, Gabber, and Prasad. So Conrad had got on the trail of pseudo-reductive groups that had sort of left uh, fallow, if you like, after they were introduced quite a while ago by Tits in the 1990s. But he came back to them because he wanted to prove statements about the about coming from number theory, basically. So that Tate-Shafarevich groups were uh, something about them. I'm not a number theorist, so I can't say exactly what, but the result of the work that they did is a very impressive book giving a classification of pseudo-reductive groups. Gave a classification of pseudo-reductive groups. And I don't have time to explain exactly the full classification. And in fact, it's not even finished. Um, so this book was supplemented by another one by Conrad and Prasad. They went even further, but there are still some lingering issues. So if anybody is interested uh, in pursuing this, it's an open problem to complete the classification in characteristic two. And I think that it's the A1 subgroups. So just rank one pseudo-reductive groups that are still unclassified. And they have lots and lots of examples, but which shows that the problem is probably quite difficult, but it is open. Okay, very impressive piece of work. I want to highlight one key result. If you hear Prasad speak about pseudo-reductive groups, he says that Conrad and Gabor had been working on this for a very long time uh, and not been making very much progress. But eventually he became involved, and the breakthrough result was the following, that uh, if, so this is a theorem of CGP, if G is a pseudo-reductive group with a split maximal torus, and we call such a group pseudo-split, then G has a Levy subgroup. And what that means is a Levy subgroup M, so that M needs to be a complement to the unipotent radical. Well, G doesn't have a unipotent radical over K, but over K bar it will do, typically. So this means if you base change the group to K bar, so you take all of the all of the equations defining G as a subgroup of GLV, consider everything over the algebraic closure, then G decomposes as a semi-direct product of M, which is now considered over K bar, with the unipotent radical of G considered over K bar. So yes, this is an absolutely key result, and you will have to consult the book if you would like to know exactly why. The reason that I'm mentioning that is because we're going to use it. So, seen Conrad speak about, he gave a lecture course in Lyon about pseudo-reductive groups. He is very animated and is worth seeing if the show comes to a town near you. But he had managed to give such a clear explanation of the overview of what was going on that I thought it might be possible to try and do something. And one thing that we found that was quite tempting as a problem was, if I can find the right thing, and I see everything's gone wrong because I've not set up different images. So let's see if it's this one. No, that is R. I think it's that. Right. So we found this in their book. And it says that the representation of the reductive groups rests on the commutative case tori. So that's referring to the fact that everything is predicated on like weights, so the highest weight theory. And then they conclude it seems difficult to say anything interesting about the representation theory of general pseudo-reductive groups. And the reason is that, yeah, I mean, even if you've got a split maximal torus, that's not, so that is not going to be a whole, what do you call it? A whole Cartan subgroup for the group. So for that reason, they came to the conclusion that you couldn't say anything. But very surprisingly, given how incredibly meticulous and accurate they were, we were able to show, we were able to do something with this. And I'll just give you the result. So this is a classification of the simple representations of a general pseudo-split pseudo-reductive group. And I'll say something about the general case, so not just the pseudo-split, but general pseudo-reductive groups in a second. So you, as part of the theory, you can always find a Cartan subgroup as the centralizer of a split maximal torus. So that's where the Cartan subgroup comes from. In a normal reductive group, the Cartan subgroup and the torus are the same. But we take this Levy subgroup that comes from the CGP theory, containing this split maximal torus, and then we conclude that the simple representations of G all have high weights mirroring the high weights that you would find from M, which is, being a Levy subgroup, is just a normal reductive subgroup. So, I mean, if you were looking at SL2, you know that uh, these things are just given by integers, and the same is true for any pseudo-reductive group with a root system of type A1. That there will be an integer, a single integer, positive integer that uh, determines the simple representation up to uh, isomorphism. It usually is the case that you get for the pseudo-reductive group of the same type as some other reductive group, the representations are much larger. And you can see there that there's a dimension formula that relates so the Lm of lambda is the reductive, sort of reductive part of this, being the Levy subgroup, and the Lc of lambda, which is no longer just a torus, that contributes to the dimension as well. So the two things are sort of multiplied together. So yeah, if G is reductive, C is the same thing as T, and all the simple representations of the torus are one-dimensional. So this kind of collapses in that case down. Right. Okay. So that was one thing we managed to do. I think I'll just say something quickly about the proof. Uh, how do you construct representations ever? You do it by induction, is the principal tool that you have. And this theorem comes from I would say, a somewhat non-trivial process of inducing from the Levy subgroup M up to the group G. One source of representations in the reductive case is by inducing from a Borel subgroup up to the group. That's a very different flavor of process because a reductive group modulo its Borel subgroup is a projective variety, and so the global sections on it end up being a finite dimension. So you get finite dimensional representations by inducing that way. Here, G over M is a quotient of two reductive of an affine group by a reductive one. That is an affine variety. When you induce, you get infinite dimensional representations. But in this particular case of the pseudo, in this, I think, be general. In this, because you're inducing through the bit that's missing, which is the unipotent radical, the structure of the induced module ends up being having a simple socle. So you can demonstrate that you end up with a simple socle when you do these inductions, and then you have to do a bit more work to kind of pin it down and say that there's only one isomorphism class for every possible weight. Okay, enough about that. One the thing that we've got onto recently, which is the topic of is the title of the talk, is what happens to the representations that come through this process. So the simple representations as you apply base change. So as we make extensions of the field, so there is no reason to suppose that the representations here are absolutely reducible. In fact, they are not. But what does turn out to be the case is that uh, they are absolutely indecomposable. But more than that, uh, they break up in what looks like, from some small examples, to be a nice to give you very nice patterns. So if I'll just try and give the most basic possible example here. So if uh, so I'll just say interested in the structure of the simple modules for G as we extend scalars, so as we extend the field. And the reason you get the reason you get sort of interesting behavior is because you're going through inseparable extensions. So if we do let's take G dash to be SL2, let's take K dash to be FP F2 even, F2 of T, K to be just F2 of T squared. So this is an inseparable extension. We get a pseudo-reductive group by doing the same process as before. We just look at this as a group over this smaller field. So G is, this is the sort of correct notation, what you get by looking at G dashed over a smaller field. Then SL2 embeds inside here because it's defined over K, and that is your levy. So the SL2 that embeds in here has an SL2 levy. So that's your M. So G, by our theorem, its representations are all determined by integers. If if n is even, then you can see that you are really factoring through a Frobenius map, which, just as we saw in the previous example, collapses the field down. And so you end up getting exactly the same representations as you do for SL2. So L of Gn actually identifies with L of Mn. But if n is odd, then the representations you get are twice the dimension. So Lg of n is 2 times Lm of n. And right, so we've got this simple representation for this pseudo-reductive group. If you make the smallest base change back to K dashed, this is no longer semi-simple, and it breaks up into, so over K dashed, if we base change this to K dash, we get a representation for L of G dashed, G over K dashed, which splits up as M with the unipotent radical. And I will just draw out what the picture is. It is a sort of simple representation for G dashed extending a simple representation for G dashed like that. So that's the picture over for this very most basic example. If you look at further examples for, let's say, if you did over, if you do this over a degree 3 extension, you end up getting pictures that look like this. I think that's right. It might be a degree 4 extension. Yeah, sort of a sort of this is sort of corresponding to this thing. I'll just sort of try and give a vague impression of how this is coming about. So if you do the same thing with this field extension, then you get a picture like this. Okay, so we were seeing these nice kind of symmetric pictures coming about through from these pseudo-reductive groups, and we wanted to see if we could describe them. One thing we were able to do is to reduce a lot of this, a lot of the question to something about the tensor products of fields. In essence, the picture that you get here is coming from the tensor product over K of this field extension with whatever field extension you're trying to use to break up the representation. And hopefully, I don't know if I can manage to say something more general in that direction. But we were led to the wanting to describe the way that purely inseparable field extensions tensor together. And there are various results across the literature about tensor products of fields, but not the exact thing that we wanted. Right, so we want to say a module is rigid. This is trying to capture the symmetry that I was talking about here. If the socle and radical series coincide. And I won't have time to write everything down. I'm just going to try and explain basically what you're doing. To find the socle series of a module, if you've drawn it out in a picture like this, to get the socle series, you go up from the bottom. So this point here is supposed to be representing the that there is a unique simple submodule. And then and that is the socle. Generally, the socle is just the sum of all of the simple submodules. If there's only one, then that's all you get. To get the socle series, you factor out the socle and then take the socle of what's left. So if I drop this, if I factor out this simple submodule, then all of these lines disappear, and then I've got these three simple modules that form the next socle layer. And you factor that out, and then you keep going. So that gives you a socle series. And the radical series is similar, but you do it from the top down. So you think, what do I have to kill to factor out to get something that is semi-simple? When you do that, you get the head. And if you continue going downwards, taking the radical of that, that gives you another series. And the radical and socle series coincide when the layers that you're pulling out end up being the same, albeit in the opposite order. Right, so we had to ask ourselves about tensor products of fields and whether they had this property of rigidity. And it's linked to Hilbert functions as well. You can express it in a number of different ways. We came up with about, I don't know, 15 different proofs that a tensor product of finite field extensions were always rigid, and they were all wrong. Eventually, we had, it took me all night and about, I don't know how many pieces of A3 paper. But let me change this image because it's wrong. I think it might be that. Yeah. Eventually, I came up with this example. Yeah, probably about 16 sides of A3 paper it took. The K and E here, if you work out the dimensions of them, this A, algebra A, ends up having 16,384 dimensions. And if you take the maximal ideal MA, it's a local algebra. MA is its Jacobson radical. Using MA, you can show that this is the series, and that's enough to see that it's not a rigid module. But we do have positive results in this direction. I'm going to just finish with the question I wanted to ask, which I haven't left as much time as I wanted, but I I'd like to ask anyway. We are absolute ignorant peasants, Mike and I, when it comes to non-commutative algebra. So we had to learn quite a lot about it. But I had a sense that there was the sort of structure of the modules we were looking at was in some kind of balance with some other structure, and indeed it is there is a double centralizer thing going on that we could show was compatible with base change. So we wanted an algebra A to do the following. So if you take a simple G module, V, and we know what those are, then there is a lemma that everybody knows very well, that the endomorphism ring of that simple module is a division ring. So we have G acting on V on one side, D acting on V on the other side. We wanted an algebra that would give you the double centralizer property. So an algebra that would have the same submodules on V, even under base change. Obviously, if it's simple, you've got no submodules at all, but this should behave under base change. with the double centralizer property, because when you have that, then you know that you can just look at the ideal structure in the division ring here, and that is mirroring in some opposite way the submodule structure here. But in order for this to work, you need an algebra A that has the same submodules as G does. There are various candidates for this. If G is connected over a field of characteristic 0, then you can always use the universal enveloping algebra. If you're over a field of characteristic P and G is still connected, then you can use the distribution algebra or the hyperalgebra. But if G is not smooth and connected over the field of positive characteristics, you can't use that because the distribution algebra only gives you something about the connected component of the identity. Okay, so this is the construction. Just suppose kg is projective, so a projective k module, and this is where we can work with any general ring k. Then the dual basis lemma, which again is something that we some very embarrassing gap in our knowledge. The dual basis lemma produces some elements of k of g, so this is the coordinate ring, and it's dual. And if you generate a subalgebra from these in k of g star, then you do get an algebra A that does all the things that you want it to. We have not found this anywhere discussed. The only other thing that we have seen is the Hopf dual. The question is, given that this is doing, suppose you have to take our word for it, this is doing all the things that the distribution algebra is doing, except it's working in all cases of whether it's non-smooth and non-connected. It is much simpler to define. You don't have to take an ideal and take sort of inverse limits and things. We don't know why people are using the much more complicated devices on offer. And it's basically, we are looking to understand the motivation there, because then maybe we can understand why this might be a deficient object in some way. So that's where we got to, and thank you for listening.
Thank you, David. I apologise for my silence and invisibility at the beginning of your talk. For some reason, Zoom didn't seem to recognise either my camera or my audio. But hopefully
you're here now, and that's what's important.
Okay. So are there any questions for David? I was intrigued by your example, David. You 1134. 16 pages and a long time doesn't seem unreasonable to come up with an example like that. I mean, where does it come from? Was there something there that put that idea in your head?
Well, I mean, as I say, we had proved this incorrectly 15 times, and it was I was had set on a path of trying to write down the 16th wrong proof. And I just got this niggling feeling, okay, well, if it is going wrong, it must be going wrong in this particular way. I think it had helped that we had, having scoured the literature, we'd found examples of commutative Artinian Gorenstein algebras. I mean, it's not difficult to find the examples. I get one very quickly, but ones which were not rigid. So then we kind of had more of a sense of what we were looking for. But yeah, I'm pretty sure it is the smallest example of
Gosh.
the I'm pretty sure that, yeah, 16,834 is the smallest possible example of a tensor product of fields which is not rigid. But yeah, it's the what happens when you tensor these things together is that you have various relations among the elements here that put them inside the maximal ideal, and then the sort of Peace powers, so squares and things, can sort of collapse them to zero. It's very without spending another 15 minutes, it's difficult to explain that. But yeah, I mean, that was the example. But yeah, 16 pieces of full paper.
Thank you. Are there any other questions or comments that anyone would like to make? No? Okay. Well, can we thank David for a very interesting talk today? Thank you very much, David.
Many thanks. Thank you for having me.